Hello! In this video, we're going to talk about the Gibbs free energy, delta G, and how that determines reaction spontaneity. Okay, but to get there, we'll go back to our definition of spontaneity. So the second law of thermodynamics says that in a spontaneous process, the entropy of the universe increases. This thing is increasing. And so that means a positive change in delta S. So delta S of the universe is positive if the process is spontaneous. So how would we go about calculating this? Well, the entropy change of the system is pretty straightforward. In the previous video, we used the standard molar entropies to calculate the change in entropy for a reaction, so that's easy to do. The problem is, how do you calculate the entropy change of the universe? Well, let's look at this. So we're looking at the entropy change of the surroundings, because that plus the entropy change of the system gives us the universe. So when we do a chemical reaction, typically the way that we interact with the surroundings is through heat, thermal energy being transferred in and out of the sample. We generally aren't moving matter or things like that in and out of the system because, you could just make your system a little bigger and then contain all the matter, and then the stuff that's going in and out is just heat. And so we know something about how temperature affects entropy. Is that if you have a higher temperature, then you have more entropy because there's more ways for the energy to arrange itself around the little quantized states. So we can say that the entropy change of the surroundings depends on how much heat went in or out of the reaction. So if you have an exothermic process, heat out, you're going to increase the entropy of the surroundings, more disorder. And so this is a positive number, which is favorable, all right? The other way, if you have an endothermic process, well, this is going to decrease the entropy of the surroundings, less disorder, and that's not so favorable, and you get a negative entropy change for the surroundings. Moral of the story, though, this entropy change of the surroundings is proportional to delta H of the system. It's just that we got to worry about this negative sign down here, because an exothermic reaction is a negative delta H, so you have to multiply that by a negative number to get a positive entropy change. Okay. Now, it turns out that the amount that the enthalpy change, delta H, of the system affects the surroundings depends on the temperature of the surroundings. If you're putting out some heat into the surroundings that are really cold, that's going to have a big effect. If you're putting some heat into surroundings that are about the same temperature, that really doesn't do much. So that's why there's this temperature in this little formula as well. And I talked about why we have the negative sign, so we're good there. Now let's put it all together. So your reaction's spontaneous if the entropy change of the universe is positive. So we just calculated something for the entropy change of the surroundings, so we can plug this in here. And then we can multiply both sides by negative t. When you multiply an inequality by a negative number, it flips the inequality. And now, okay, we know delta H. We know delta S for the system. That's something we can calculate from these values that are in tables, so that's easy. We know the temperature. We don't know this. So what we're going to do is we'll call this a new function. This is the Gibbs free energy, and sure, it's equal to negative T times delta S of the universe. Nobody ever really thinks about that. We just think of what is the Gibbs free energy for this process. So now, the big kicker here is that delta G is negative for a spontaneous process, right? So less than 0. One nuance is that this is for constant temperature processes. You don't, say you're at equilibrium, you don't want the temperature moving all around because that would change things. And it's also for constant pressure. Ultimately, this comes from heat, and heat is equal to delta H only at constant pressure. So, Gibbs free energy, you can think of it as the free energy available to do work. What are you going to do with this reaction? It's all contained in delta G, both the entropic and the enthalpic contributions. Fun words. And again, delta G is the ultimate decider of whether some reaction is going to be spontaneous, right? So if your reaction has a negative delta G, then it's going to proceed spontaneously forward. That's easy. If your delta G is positive, then your reaction's not spontaneous as written. However, if you flip the reaction, you're going to flip the sign of delta G, And so that implies that if you have a positive delta G, that the reverse reaction is going to happen spontaneously. And then at equilibrium, delta G is 0. That hopefully makes sense. So delta G does a good job of balancing these kind of competing effects from both enthalpy and entropy. So a negative enthalpy is favorable because it increases the entropy of the surroundings. A positive entropy of the reaction is favorable because it increases entropy of the reaction itself. So if you have both of these in this form, then your reaction is always going to be spontaneous because mathematically delta G will always be negative. Let me do the bottom case next. I think it's the other way, and it's a little simpler. Whereas if you have an endothermic reaction that makes more order, nothing here is favorable. And so overall, your reaction is always going to have a positive delta G and not be spontaneous in the direction that it's written. Now, in the middle, then it really comes down to how big is each one of these, right? If you have a favorable delta H, but an unfavorable delta S, then the relative magnitude of the two terms matters. It's spontaneous when this part's bigger. Whereas if you have an unfavorable delta H, but a favorable delta S, then now you just need this term to be bigger, right? Which happens to be multiplied by the temperature. So the temperature is going to play a big role here because that affects the relative magnitude of these two terms if you're in a state where one of these two is not favorable. So let's do that, right? So say we have calcium carbonate solid, and we're going to make calcium oxide and carbon dioxide. Now, I already calculated delta H and delta S for this. Just you use the values that are in the tables, and you do final minus initial, etc. We talked about that in the previous video. All right, let me scoot this up. So let's just show a couple examples here. So say we're at 298 K, which is 25 Celsius. So we just plug the numbers in, just from above, into this equation for the Gibbs free energy. And we see that this is a positive number at this temperature. So we can conclude that at this temperature, under standard conditions, this is not a spontaneous reaction. One big thing to keep in mind here is that almost always your delta H is going to be in kilojoules, and your delta S is going to be in joules, so you have to make a match. I usually convert the joules to kilojoules, because generally this comes out in kilojoules, and it just works out nicer if you do that. But overall, just make sure the units match. Okay, let's try a different temperature. So we do the same thing, and we just throw in a new temperature, and now we get a negative delta G. So at this temperature, your reaction is spontaneous. Again, under standard conditions. So thinking about standard conditions, when we defined how to calculate delta H and delta S, we said the standard state was relative to 1 bar, 1 molar, and 25 C. So these have a temperature attached to them. Now, when we're at 25 C here, this works out just fine. When we're down here, we need to make an assumption here. We need to assume that whatever the values are for delta H and delta S, that they're temperature independent. Now, this is kind of an assumption. It's not that great of an assumption. But for our purposes in Gen Chem, in trying to just figure out how spontaneity depends on temperature and kind of get an idea about what that temperature might be, that's fine. So we're going to make that assumption in this course and just move on. Now, we saw that at 1200 Kelvin, this reaction is spontaneous. And at 298, it's not. So where does the line sit in between these two for where it becomes spontaneous versus not? So let's calculate that. At what temperature does this become spontaneous? Well, we need a temperature that's right in between a negative delta G and a positive delta G, and that's called 0. And so we'll just set this equal to 0, and then we can rearrange the equation to solve for temperature. And then let's plug the numbers in. All right, we have our delta H, we have our delta S. Make sure you make the units match. And then you'll get some number in Kelvin, which for this reaction is 835 Celsius. So that's the line between spontaneous and non-spontaneous. Next thing you got to figure out is on which side of the line is it spontaneous, the higher temperature or the lower temperature. So for this reaction, delta H is positive, and that's the non-favorable one, so that goes here. Delta S is positive, which is favorable, so delta S is positive here. So that means this negative sign will send this whole term negative. And now we need this negative term to override the unfavorable positive delta H. So more of this is better. So more of this means a higher temperature. So therefore, this will be spontaneous at a higher temperature than 835 C. And, at that temperature at 835 C, it should be right about equilibrium because delta G is 0. Okay. So one final note is that below this temperature, we declare this reaction as non-spontaneous, even though there's still carbon dioxide gas that's produced. We have to draw a line for spontaneous, and it doesn't really make sense for that line to be you made a tiny little bit of product. We're talking about standard states. Standard state is 1 bar. So when we say it's spontaneous, that means you make 1 bar of products. So you can make less than that and still definitely make a good amount of products, but it's just not going to be declared spontaneous according to delta G. So that's something else to keep in mind, that you can have the reaction go a little bit, but it can still be declared non-spontaneous because you didn't make 1 molar. This is especially notable for the KSP solubility problems. You have some salt that's barely soluble, but it still does make ions in solution, even though they're at a small concentration. And so this will be listed as a non-spontaneous reaction with a positive delta G, but it does actually do something that you can use. So just keep that one in mind. And that's all I have for now. Thanks for watching.